Hello everyone. Welcome to my channel Chemistry by ANR. This is the next part of the chapter Coordination Compounds and the text is from NCERT. Do remember, if you really have to score good in your board exam, you actually have to go through NCERT first. These are some important terminologies like the coordination entity. Coordination entity is the part which is also known as the coordination sphere. It is also known as the coordination sphere, and this coordination sphere has a central metal atom or ion. So it has a central metal atom or ion which is bonded to fixed number of ions or molecules which are termed as ligands. If we see these compounds, say COCl3NH3 whole thrice. So CO, this is your central metal atom. Okay, so this is your central metal atom or ion, and these are the ligands. These are the ligands, that is atoms or groups that are surrounding the central metal atom or ion and which is bonded to the central metal atom directly. Now, I said that there is something called coordination number in the previous module. We are going to talk about it in this module once again. So they are surrounded by types of atoms. Let us see Cl minus. Cl minus is negatively charged. NH3 is neutral. So the central metal atom or ion has fixed number of ions or groups that are bound in a definite geometry, which is known as the coordination polyhedra. And let us see, like over here, what are the oxidation states? In this compound, it is Ni2 plus, CO3 plus in the next, and Fe3 plus in the next. How do we know this? To know this, we need to know about the ligands as well. So let me tell you about the ligands. The ligands are the atoms or groups of atoms that are bonded to the central metal atom or ion. So ions or molecules bound to the central metal atom or ion in the coordination entity, they are known as ligands. These ligands can be negatively charged, can be positively charged, can be neutral atoms as well. Now here this line, these central atoms or ions are also referred to as Lewis acid. Why they are referred to as Lewis acid? Because they are electron deficit. That's why they are also referred to as Lewis acids, which are lone pair acceptors. They are lone pair acceptors, and this lone pair is donated by the ligands. Now these ligands like Cl minus is anionic ligand, H2O and H3 they are neutral ligands. There are larger ligands also. Here ethylene diamine, this is also abbreviated as EN. Ethylene diamine. Now always keep in mind that the ligand should have something for which it is getting bonded to the central metal atom or ion. In this example Cl minus, you can see the negative charge. In case of H2O, oxygen has a lone pair which can be donated to the vacant orbital of the central metal atom or ion. In NH3 nitrogen has a lone pair. In ethylene diamine, this is named as ethylene diamine. En is the abbreviation, or it is ethane 1,2 diamine. Remember one more thing, that in ethane 1,2 diamine, it is a single M. But the moment you are naming NH3 as a ligand, it is amine, and here it is having a double M. H2O is named as aqua when you are naming it. In nomenclature, again, in the next module, we will be again talking about these things. But just get to know all about ligands. H2O, NH3, they are neutral ligands. They are named in this manner. Anionic ligands are having O, like Cl minus. It will be known as chlorido, bromido, iodido, like this. If it is say En, it is ethylene diamine or ethane 1,2 diamine, which is used in nomenclature. Now, there are other ligands as well, like we need to know what is the denticity of ligand. This part will be talking about denticity of ligand. Before we go to this part, I have actually mentioned about the oxidation state of metal. So that we need to just see once. See, in this compound, which is a coordination complex where nickel is the central metal atom, Cl2, H2O whole 4. So Cl minus and H2O are the ligands. Now, if I need to find out what is the oxidation state of nickel over here, I will consider nickel oxidation state to be X. Let us assume to be X. Cl, for each Cl it is -1. For 2 Cl it will be -2. H2O is a neutral ligand. It doesn't have any charge, which is equal to the overall charge is not there. So it is 0 and X is equal to +2. So this is nickel +2. That's why we can see over here Ni2+. In the next one, here, they have given CO3 plus. Let us see how it is CO3 plus. So this is your cobalt. We will find out how it is CO3 plus. Let us assume it to be X, oxidation state of CO to be X. For 1 Cl, it is -1. NH3 is neutral. Overall charge is +2. So I am writing +2. So X is equal to +3. Likewise. Here again Fe, if I assume it to be X, Cn means Cn -1, so -6 is equal to -3 or X is equal to +3. So we have got Fe3+. This is how we are going to calculate the oxidation number of the central metal atom or ion. Now, denticity of ligand means how many bonds the ligand is able to form with the central metal atom or ion. Or we can say that how many donor sites, donor atoms are there in the ligand. So when a ligand is bound to the central metal atom by a single donor, there is only one donor, Cl minus may only Cl. In H2O, it is oxygen which has a lone pair. In NH3, it is nitrogen which is having the lone pair. So the donor site or donor atom is nitrogen. And since it contains a single donor, it is known as monodentate or unidentate ligand. It is also termed as monodentate ligand. So denticity means how many coordinate bond it is able to form. Now, when a ligand is bound through two donor atoms, it has two donor sites, like over here in ethane 1,2 diamine, the 2 nitrogen, because the 2 nitrogen has lone pair. So this is one donor and this is the other donor by which it can form coordinate bond to the central metal atom or ion, and they are known as didentate ligand, or this can also be written as bidentate ligand, which has denticity 2. There are two donor atoms or donor sites. Now, if there are many or several donor atoms, they are known as polydentate. That means greater than 2, of course. So here in polydentate ligand, EDTA4- is one such example, which means ethylene diamine tetraacetate ion. This is the structure. You can see nitrogen has lone pair. Nitrogen has lone pair above it, so we will make lone pair over here. And ethylene diamine tetraacetate, how the structure is drawn, let us see. Ethylene diamine is CH2, CH2, NH2, and over here it is NH2, En, which we have said ethylene diamine or ethane 1,2 diamine. Now, if I say ethylene diamine tetraacetate, so here it is CH2, CH2. There are two NH2. I'm writing N and giving the two valencies like this. So again, the two valencies like this, lone pair above nitrogen. Tetra means 4. Acetate is CH3COO minus. When it gets bonded over here, it gets bonded as CH2COO minus. So the negative charge is again the donor site. So here there are 4 such CH2COO minus, and that is what we are seeing. Now what is the denticity of EDTA4 minus, ethylene diamine tetraacetate ion? This is one donor, this is second, third, fourth, fifth, sixth. So this is hexadentate ligand. So EDTA4 minus is hexadentate ligand. It has denticity equal to 6. And these types of ligands, be it two donor site, be it more than that, these types of donor, that means didentate and polydentate ligands, if they actually form the bond with the metal atoms simultaneously, they are actually known as chelating ligand. That means they form a ring-like structure. They form ring-like structure because they are bonded simultaneously. Two atoms bonded together. That means it forms a ring-like structure for which these chelating ligands are forming chelating complex which are having extra stability due to high entropy. Due to high entropy, they have extra stability. So there are different type of ligands. We have seen another type is ambidentate ligand. Ambi means both. So here again it contains two donor site, but the two donor site do not simultaneously form the bond with the central metal atom, and that is the difference between a didentate and an ambidentate ligand. Didentate also has two donor sites, ambidentate also have two donor sites, but in case of didentate ligand, the two atoms which are donors can simultaneously bind to the central metal atom or ion, but in ambidentate ligand, the two donors can actually bind one at a time. They can bind one at a time. So that is the reason, on account of resonating forms, like if I say Cn minus on account of resonating forms, in one of the structure carbon gets the negative charge and there is a bond between the metal atom and Cn, and it can be named as cyanido as a ligand when carbon is acting as the donor. In another resonating form, the nitrogen will act as the donor because the negative charge will reside over the nitrogen and it will bond as Nc with the central metal atom or ion, and it will be named as isocyanide. And let us see over here in NO2 minus, here when nitrogen is acting as the donor atom, it is nitrito N. And when oxygen is acting as the donor atom, it is nitrito O. That means the negative charge can reside over nitrogen as well as over oxygen depending on the resonating forms. In which resonating form it is residing over nitrogen, it will form nitrito N. If it resides over oxygen, it will form nitrito O. And with SCN minus again, the negative charge residing over sulfur will form thiocyanate, and the negative charge residing over nitrogen will form isothiocyanate. It is isothiocyanate, or you can write thiocyanate S or thiocyanate N. Either you can write thiocyanate and isothiocyanate, or you can write thiocyanate S or thiocyanate N in this manner. So, the coordination number depends on denticity of the ligand. That means how many bond it is actually forming. It's a number of ligand donor atoms to which the metal is directly bonded. Like, let us apply PtCl6 2 minus. Here these are monodentate ligand and they are 6 in number. So, coordination number is equal to 6. Now over here again monodentate ligand 4 in number, coordination number is 4. But for bidentate ligand, oxalate ions, oxalato, each is 2 minus, there are 3. So the coordination number is equal to 3 into minus, 2. They are 2 in number, so I will not give that minus sign. So I'll say 3 into 2, which is equal to 6. Valency. How do we write? C2O4 2 minus. So valency, what we'll say? 2. So 3 2s are 6. Over here, ethane 1, 2 diamine. It again has bidentate ligand. It has denticity equal to 2. So how many such ligands are there? 3. Denticity is 2. So 3 2s are 6. So they will form octahedral complexes. So these are having coordination number equal to 6 because C2O4 2 minus and ethane 1, 2 diamine is a didentate ligand. They are didentate ligands. Now the coordination sphere, what it is, the non-ionizable part and the part which is given in the square bracket is known as the coordination sphere that we have already discussed. It's also known as the coordination polyhedra. So coordination sphere. When you talk about three-dimensional arrangement of the atoms in space or groups of atoms in space around the central metal atom or ion, then it is coordination polyhedra. And depending on the coordination number, like for coordination number equal to 6, it is octahedral. Coordination number equal to 4, it can be tetrahedral or square planar. Coordination number equal to 5, it can be trigonal, bipyramidal or square pyramidal. Finding the oxidation number of central atom that we have seen, it is represented by the Roman numeral in parenthesis. So here how to find copper, if I consider to be oxidation number is X and Cn minus 1, there are 4 such. So minus 4 is equal to overall charge minus 3. So X is equal to plus 1. So copper has plus 1 oxidation number. So this is how it is written. Now what is lepticity of complex? Lepticity of complex means how many types of or how many kinds of ligands are surrounding the central metal atom or ion. If there is only one kind of ligand surrounding the central metal atom or ion, they are homoleptic, and if there are more than one kind of ligand surrounding the central metal atom or ion, they are heteroleptic. Here only amine is there. It's amine as ligand, double M, and so it is homoleptic. But here it is amine with a double M as well as chlorido, and so it is heteroleptic, more than one kind of donor atom, so it is heteroleptic. So these are the two terms, one is homoleptic and the other is heteroleptic, depending on how many kind of donor atoms are there attached to the central metal atom or ion. Now seeing the exercise question related to your session 1 and session 2, we have seen the postulates of Werner in the previous part. We have seen more salt, and in this part also, in the previous part also, the concept is there like FeSO4 solution when it is mixed with NH4 whole twice SO4 in 1:1 molar ratio. Ferrous sulfate, ammonium sulfate, it gives you the test of Fe2 plus ion. Why? Because it forms more salt with a formula of ferrous sulfate, ammonium sulfate, hexahydrate. and this is known as more salt, and this is a double salt. This is a double salt with two simple salts arranged or chemically combined in a fixed ratio. We can see 1:1 molar ratio. Double salt completely ionizes in aqueous solution, for which when it completely ionizes, it gives you what? It gives you in aqueous solution, it gives you Fe2 plus aqueous, for which you get the test for Fe2 plus. You get SO4 2 minus 2 moles aqueous. You get the test of sulfate, and you also get NH4 plus aqueous. You get the test for ammonium ion as well. Now, when copper sulfate solution mixed with aqueous ammonia, you should know one thing, that aqueous ammonia actually means NH4OH in 1:4 molar ratio. Now, when it is 1:4 molar ratio, remember it forms a complex which is CuNH3 whole 4SO4 is the counter ion. So here, if anyone asks you what is the primary valency, how many sulfate ion is obtained, that is the primary valency. What is the secondary valence? Secondary valence is the coordination number, which is directly attached to the central metal atom NH3, 4 in number. That. Now the question is, when CuSO4 solution is mixed with aqueous ammonia in this ratio, it does not give the test of Cu2 plus. Why? Because this is your coordination entity. And what is that? Here it is CuNH3 whole 4. It is written at first, so it is the positive part, and it has 2 plus in aqueous solution, and this has SO4 2 minus in aqueous solution, the sulfate ion, the counter ion. Since this is the coordination entity, and the coordination entity is non-ionizable, so you will not get the test for Cu2 plus over here. So it is non-ionizable part. So you will not get the test of Cu2 plus. Next, explain with 2 examples. Coordination entity, ligand, coordination number, coordination polyhedron, homoleptic, heteroleptic. These terms you have seen over here. What is unidentate, bidentate, ambidentate? You have seen over here. Do practice what is the difference between a didentate and ambidentate ligand, which I have already told you. Specify the oxidation numbers. Let us see one by one. Here obviously of the central metal atom they are talking about. So if I say this one, so about cobalt, let me consider it to be X, and H2O is neutral, En is neutral, but Cn is -1, which is equal to +2. So X is equal to +3. First one, X is equal to +3. Next one, number 2. Let's see over here. Now CO, let us assume to be X, Br means -1, 2 are there, -2 is equal to +1 overall charge. So X is equal to +3. Third one, it says PtCl4. If I consider Pt to be X, for 4Cl -4 equal to -2, X is equal to +2. Next, Cr, if we consider, fourth one, this one. Fourth one, potassium is ionizable, but iron is non-ionizable, and oxidation number means of iron. So if I consider this as coordination entity, it will be FeCN whole 6, counterpart will be 3 minus charge. So here if I consider this to be X, so X, Cn will have -6 equal to -3, or X is equal to +3. Fifth one, chromium can be taken as X, and NH3 is neutral, and Cl3 is -3, no charge over there, so X is equal to +3. Now this is how you are going to find out the oxidation numbers. In the next module, we are going to discuss about nomenclature, its rule, and till then, bye all of you.